Today, we'll be doing thermochemistry. At the beginning of the semester, when we decided to define chemistry, we defined chemistry as the study of matter and its constitution and its relation to energy. And therefore, in this particular topic, we are going to deal with energy. So the question is, what is energy? And the answer to that lies in the fact that energy is the capacity to do work. Because it is the capacity to do work, it has the same units as work. And so, with that, we are going to see that in chemical reactions, heat can either be evolved or absorbed. There is always a system and a surrounding. A system is the area or the region where the experimentation is taking place, and all other regions or space around that particular experimental place is called as the surroundings. Energy can be either exothermic, released to the surroundings, endothermic, absorbed from the surroundings, and therefore this is useful in determining the nature of energy transfers. Then we have to understand the sign conventions of thermodynamics. And then, of course, we are going to do at least one small problem on how to use specific heat capacity in calculations of energy transfers when temperature changes occurs. Now, before we go any further, we have to first define how we are going to cut this chapter into small bits so that you can understand the whole concept behind it without overpowering any yourself. So now, first thing we ask ourselves, we know that we are talking about energy, and we come to matter a little bit later on. But we have to first define what type of energy it is. We have got energy is the capacity to do work. And we define energy in two terms, kinetic and potential energy. Kinetic energy is due to the motion of particles, like a motion of particles, which is thermal, mechanical, for example, running a car, electrons, electric current moving through a conductor, sound, it is acoustic compression and expansion. And the second type of energy is, of course, the potential energy, which is associated with the position, state, or composition of substances, and then, of course, the chemical energy. One of the best ways to actually understand the relationship between potential and kinetic energy is to study the movement of a pendulum. If the pendulum swings high, then it goes up to a certain height, and then once you release it from that particular height, it comes down, swinging down, reaches a minimum, and then goes up again. And this is a transformation of energy from potential to kinetic energy. And during this process, we have to apply the law of mass conservation of energy, which says that energy can neither be created nor destroyed, but it can be transformed. Now, the next thing we have to remember is that when energy is transformed, then all the transformations take place in the form of heat, and heat can be measured. So when we do chemical reactions, we are changing basically the chemical potential energy that is there. And so we have the thermal energy at the molecular level, and the chemical potential energy is associated with the arrangement of particles that are there. Now, generally speaking, the transfer of thermal energy is always from hot to cold, higher kinetic energy to lower kinetic energy, and the amount of energy transformed is designated by the symbol Q. Now, heat versus temperature. Heat is the transfer of energy from a hotter body to a colder object, and it is an extensive property. Temperature is the measure of the intensity of heat and not the amount. So temperature is an intensive property. A drop of boiling water versus a pot of boiling water. Both have the same temperature, but different heat content. Now, next thing that everybody should know are the terms that are there. System and surroundings. Object collection of objects used in a study. It can be an open system, a closed system, or an isolated system. Open system, if you leave it in the lab and do it, that's an open system. Closed system, if you cover that up and don't let anything else go in or out, then it's a closed system. But an isolated system is one if you take a styrofoam cup and put anything inside it and close it and do not allow any heat to come out or go in, then it's called as an isolated system. Surroundings, all the rest of the universe outside the system is considered as the surroundings. Energy can be transferred from the surroundings to the system, or can be lost from the system through the surroundings that are there. Now, whenever there is a change in heat energy transformed from one system to the other. The best example is if you take a hot water and add cold water to it, start immediately that the hot water is going to lose heat and the cold water is going to get warmer. So warmer till both of them reach the same temperature. When the same temperature is reached, then we say that a thermal equilibrium has been established. And the thermal equilibrium that is established is a dynamic equilibrium because both heat loss and heat gain will be going on simultaneously. An equilibrium is a physical term which says it maintains balance. A thermal equilibrium, the object with the temperature increase has gained thermal energy and the object with the temperature decrease has lost energy. And so here you have different types of energy systems, exothermic, endothermic, and the exothermic means Q is less than 0 because it is lost. Endothermic means it is gained. And the best example for you to know or understand exothermic, endothermic reactions and also exothermic and endothermic systems is just hold a cube of ice in your hand, and what happens is you feel cold because heat is being withdrawn from your body. And what happens when the heat is withdrawn from the body? The ice starts melting. And so the ice gains heat, therefore it melts while you lost heat and you feel cold. Now, specific heat capacity. Now, we know that the amount of heat absorbed or evolved by a substance, by any material, is directly proportional to the mass of the material, the specific heat of the material, and the temperature change that is there. And therefore, we say that the heat energy is transferred, is required to raise the temperature of 1 gram of a substance by 1 Kelvin. That is defined as the specific heat capacity. If the substance is water, then of course you will get the definition of a calorie within a specific range of temperature. The specific heat depends upon the quantity of the substance, identity of the material, and the size of the temperature's change. Now here you have different materials and you have their different values that are the specific heats of same material, different phases, that means different states, And so we can use this information to calculate out what is the change that is taking place. And so almost all substances which are metallic heat conductors, they have very low specific heat as compared to water, which has a very high specific heat. And therefore, the property of water having a high specific heat is very good because it helps us not to overheat, because it takes 540 joules to change 1 gram of water to vapor. So now we see the expression Q is equal to Cm delta T. Q is the heat energy gained or lost, M is the mass of a substance, C is the specific heat, and delta T is the change in temperature. Remember that whenever you come across the symbol delta, it is always T final minus T initial. Now you can work out a problem at your desk and the answer is given. So you have 50 grams of water is heated from 25.3 to 33.7 degrees. What is the amount of heat energy that has been transferred to the water? So we have Q is equal to C, which is 4.184 joules, multiplied by mass, which is 50 grams, and delta T is, you can calculate it as 33.7 take away 25.3, which is 8.4 degrees. Now, we can write it in degrees C or Kelvin because the difference is the same in both scales. And so when you multiply all the terms, you get the answer 1757.3 joules. The sign is positive. Why is it positive? Because the thermal energy has increased. How do we know the thermal energy has increased? We know it because the temperature rose. The thermometer gave a higher value. Then there's other laws of heat, aspects of energy transferred, and that is the conservation of energy in an isolated system. Whenever you have an isolated system, the changes in energy within the system must be such that the sum total must equal 0. Like density, specific heat is an intensive property of a pure substance and can be calculated experimentally. Now, the energy changes delta U is equal to U final minus U initial. Endothermic reactions absorb heat. Heat flows from surroundings into the reaction. Exothermic heat flows out of the system that is there. And here is a middle, a very simple one, which the same type of experiment is performed in the lab to find out the specific heat of a metal. So if you put a hot metal into a cold water, you know that the temperature will rise of the cold water, whereas the hot metal will cool down. And the amount of temperature, final temperature, because this is a heterogeneous mixture, will have the same temperature that is there. And using that, we can calculate the specific heat of the unknown metal, because we have heat lost is equal to heat gain. Hot metal will lose heat, so we can write it as Q is equal to MC delta T, T final minus T initial, and change that to T initial minus T final, and then solve the equation. Why we can solve the equation that easily? Because of the law that energy can neither be created nor destroyed. And so there are some worked examples over here, and I would expect you to please go through it, and we will almost complete this particular share, because I don't think, yes, these are all working examples, and so you can share. Do it as a practice.